So hello everyone, welcome to lecture 11 on finite element method. In this lecture, we want to continue on the same journey basically that we had together, and we started together from a differential equation from the strong form. And then we talked that what we want to do first, or what we want to get as our first station, is to go to the weak form. So this is what we want to do. And then we learned how to do this. We learned how to go from strong to weak form, let's say in a mathematical sense. And we were doing an example on that, and we finished the previous lecture. So we are still here, okay? Or we are still in this process. We know how to do it, and we are doing an example basically, or we continue the example that we started last time. Okay, this is a roadmap of finite element method, and this is exactly the roadmap we are going to follow in the future lectures. So again, you will see it again and again, but this is where we are. That's it. Just to give you a little reminder, we had talked about different approximations in FEM. So you have this so-called, let's say, solution approximation, you have equation approximation, and you have some sort of input approximation when you are dealing with something like the finite element method. We also discussed about the strong form, or the differential equation governing the finite element method. The governing equation of the finite element method is basically the balance of forces, if you want. So it is a force balance equation. For us, this force balance equation would look like a differential equation. So you can prove that a force balance equation, or governing equations of mechanics, they are differential equations eventually. And these differential equations, they have, let's say, a form, we call it strong form, and they are subject to some boundary conditions. Again, as we did before in a truss structure, if you have a displacement type boundary condition, you would call it a Dirichlet boundary condition. If you apply a force, or in this case, the force would look something like the derivative of displacement, or a strain, you can see that. So if you think of a force is immediately proportional to u prime, and u prime is basically strain. So either you apply displacement, or you apply the derivative of displacement, which is more or less like force, and that would be called the Neumann type boundary conditions. And also we talked about these two examples. Let's say if you think of a hanging beam or a standing beam, these are two examples where this is exactly the differential equation, and for these we also have the analytical solution, and we can solve that. So long story short, this is where we are. We have a strong form. We know the strong form is a differential equation. In our case, we are specifically talking about this second order differential equation, but it could also be more complex than that. The finite element method itself as a methodology can be used for differential equations. That's not what we do here. We specifically focus for now on this differential equation, but the methodology itself is the same thing. And then also, again, for simplicity, we assume that the domain of, let's say, our geometry is between 0 and 1. This is another simplification which doesn't change the methodology. You could have assumed this is between -5 and 10. It doesn't matter really how it is. And then in those ends, so at the end point, you have some sort of boundary condition. In this example, we assume on the left, you have a Dirichlet type boundary condition. On the right, you have a Neumann type boundary condition. Again, this is an example. So now, having said that, let's say we have this strong form as an example. What we want to do is to derive the weak form. And we said in order to derive the weak form, we need to define this so-called test function with specific properties. It's arbitrary, it's continuous, and it's also 0 at Dirichlet boundary condition. And then what you do is to multiply first the differential equation by the test function, then you integrate it, and then you separate these integrals, and you use this identity basically here. And eventually, if you do all of that, you would end up with this form. And this form essentially is your weak form. So if you think about what we had here, this is the strong form. And you can see the strong form is a differential equation, is a second order differential equation. On the other hand, weak form here, it is an integral equation. And the derivatives of u are only first derivative. They are not second derivatives. So this is very important because basically it allows you to have a wider family of u here, because you only need this to be differentiable once. It doesn't have to be twice differentiable. In other words, if you assume that u here is a quadratic function, here you can also work with lines. So a piecewise linear function could also be an option for you, and that is something which is also very interesting for us, and that's our starting point. And then again, if we analyze this weak form, it has this so-called internal contribution, then it has the external contribution over the domain, and then it has the external contribution over the boundary of the domain. We also shortly talked about the so-called Bubnov-Gyorkin and isoparametric concept. So that is the way we are going. All that means for you is that x, u, and w, they follow the same representation. They follow the same approximation. We can approximate them differently, but we do not. We use the same approximation for all the three of them. Okay, and now this is the example that we started together. So let's say you have this problem as our strong form. This is our example here. And what we want to do is to solve this using, let's say, the weak form, using the finite element method, and learn the bits and pieces of the finite element method by doing this. Now, for this one in particular, obviously, we have also an analytical solution. The analytical solution satisfying the boundary condition is this. So you have this quadratic function. This is your analytical solution. And what we want to do next is to start from this, from the weak form. And if you use the boundary condition, this would be your weak form. So this is basically your shorter weak form or reduced weak form. And we want to compute approximate solution. This is the exercise we want to do. And we want to take that solution from different spaces. Okay. So this is the example, or this is the extension of that example. We have this function, we know the analytical solution. Using the weak form, we want to solve the solution to this example based on different approximations. The first approximation we played with was a linear approximation, a one-piece linear approximation. And then we started to look into a two-piece linear approximation, which is uniform in the sense that we split the two pieces equally. So it is, the point is exactly in the middle of the domain. And now we want to proceed on that. We talk about two-piece nonlinear, and then two-piece generic, and then we go to higher order approximations. But this is exactly the example we want to proceed with. All right, so if we had a one-piece linear approximation, if you remember, well, basically you take a line or a piece of line between 0 and 1, and a linear function between 0 and 1, it would look like this. Remember, it's like f equals, I don't know, mx plus b. This is a linear function. This is exactly that. So it would be c1x plus c2. That's a linear piece. this is your test function, and then you also use the same linear the same space basically. So because this is linear, we also use linear for u. So this would be also some parameters d1 and d2, which gives you a linear approximation of u. And then you insert the boundary conditions, you calculate w prime u prime, you insert it into the differential equation, you solve it, and then you get this. So this is what we did previously. This is basically u equals 1/2 x. As you can see, this is a line. This is a one-piece line, or otherwise a linear approximation. So the fact that it's a line, obviously it is worse than the quadratic curve itself, but let's say surprisingly well, you can see that it hits the two endpoints. So it's not a bad approximation. It's a very nice approximation to have that quadratic curve. So if you had a quadratic curve and you had to choose a linear approximation of it, this is a very meaningful approximation. Okay. The important thing though here is that you should remember that in order to get the line here, we started from this equation, which is an integral equation. So I think this is the more important message, that the line in itself, it doesn't know anything about the differential equation. It just knows this integral. And that is kind of the message I want to pass, that the integral or the weak form itself is the approximation basically, and then the rest is the solution to that approximation. Okay, so as you can see here, the Dirichlet boundary condition is strongly satisfied because you hit the points, and then Neumann boundary conditions are not strongly satisfied because the derivative could be different at Neumann-like boundary condition. So that was a one-piece linear approximation, and then we want to do a two-piece linear approximation, which is uniform in the sense that the left and right piece, they are equal, so we split the domain exactly in the middle. Now, if you want to do that, you can see that the domain here is exactly split in the middle. So x goes from 0 to 1/2, and then from 1/2 to 1. Now, from 0 to 1/2, w would be c1x plus c2. And u would be e1x plus e2. So it's a line, again, it's a linear approximation, remember? And also from 1/2 to 1, it's another linear approximation. So let's say there is a line here, maybe, and there's a line here. So this is, again, a line equation for w and u, but the parameters are different. So here you would have 8 parameters, let's say naively speaking. But then in these 8 parameters, you insert the boundary conditions themselves, but also you impose the continuity of the pieces. Okay, so if you calculate, let's say, a displacement, you don't want a displacement jump at this point, right? So let's say if this is your approximation, this could be your right piece, this could be your left piece, but here you want it to be continuous. So you impose that continuity, and that gives you also a relationship between the parameters. So you get 2 more equations, and basically now you had 8 unknowns. 2 of them are gone because of the boundary conditions. 2 of them are gone because of the continuity equations. So you have 4 unknowns left. Now, what we want to do is to exactly proceed as we did before. We want to insert this into the weak form and solve the problem. So this is your weak form basically. And now if you use the functions u and w as you have here, this would be now your weak form down here. Okay, so this is basically splitting we didn't do anything particular here. We just split the domain. Instead of saying that we go from 0 to 1 because it's a two-piece linear, and we know these are the pieces. We just do it like this. So we split the integrals. And now in these integrals, we know, let's say here, we will use the parts that are corresponding to the first piece. And then let's say in the second integral, we use the parts that are corresponding to the second piece. So this is how it works. And that is where we stopped in the last lecture. So what I want to do next is to basically continue on that. Okay, so let's look at this. From what you have here, what is W prime and U prime? So in the first piece, you can see that W prime is C1. In the second piece, W prime is D1, right? It's just a derivative basically. So the derivative of a constant is 0, so it doesn't enter the equation. Now, we have these relations for F2 and D2. So later when we need them on the right-hand side, we also remember that. And on the first piece now, U prime is E1. And on the second one is F1. Okay. So W here on the first piece is basically this, is D1X plus D2. But then you also know that D2 is 1/2 of C1 minus D1. So instead of W, you would say D1X plus 1/2 of C1 minus D1. And here, instead of W, you would just insert. And sorry, I think yes, wait. In the first one here, this is the first one, W is C1X plus C2. I just miswrote them. So let me, since I wrote them, I will just copy this. What I wrote here was for the second integral, right? Okay, so for the first integral from 0 to 0.5, W is C1X plus C2. C2 is 0, so it is C1X. For the second integral, on the other hand, W is D1X plus D2, and D2 is this. So we already have this relation, and we insert that here. All right, so we continue on that. And just clean the, or maybe I keep the U part, I remove this. So just remember the U parts here. This is the way that U is prescribed. So if we could calculate E1, F1, and F2, then we already know, let's say what U is. Okay. So this is what we want to do next. All right. So let's see if it works. So what I want to do now is to basically write this integral again, but in terms of these parameters. So you have an integral from 0 to 0.5. Now W prime U prime would be C1 E1. dx plus integral from, let's say, 0.5 to 1 d1 f1 dx. And that thing would be equal integral from 0 to 0.5 c1x dx plus integral from 0.5 to 1 d1x plus 1/2 of c1 minus d1. So the whole thing here, d1, let me just copy d1x here. All right. Now, these, let's say, mathematical details or intermediate steps, obviously, I do it now for this example in this level of details. For the next example, we go through them much quicker. But I want you to see every little piece of the, let's say, the process, at least for the first time. Okay, so this is how it is done. Now that you have these integrals, all you need to do is to calculate them. So if you want to calculate these integrals, it's pretty simple. So here you get c1 e1 x. So basically this term altogether, it gives you c1 e1 x from 0 to 0.5. So that gives you 1/2 of c1 e1. Okay, so that's first term. So the first integral is 1/2 of c1 e1 plus the second integral is the same. So it's going to be d1 f1 x from 1/2 to 1, which would be also 1/2 of d1 f1. Equal, what do we get on the right hand side? This thing would be 1/2 of c1 x squared from 0 to 1/2. So 1/2 to the power 2, that gives you 1/4 times 1/2, that gives you 1/8. So this thing would be 1/8 of c1. So the first term on the right hand side, it translates to 1/8 of c1 plus, now you do the integration here. So you would have 1/2 of d1 x squared, let's say from 1/2 to 1, plus that second term, which is 1/2 of c1 minus d1 x from 1/2 to 1. So this part altogether, it gives you 1/4 c1 minus d1. And the first part altogether, it gives you 3/8 of d1. Okay, so you can see it's 3/8 if you pay attention to the limits. It's basically 1 minus 1/4, that is 3/4, and then you have 1/2 in front, so it is 3/8. Okay, so these two are the terms for the for the last integral, so if I remember that correctly, it was 3/8 d1 plus 1/4 c1 minus d1. All right, so that's it really. Now, instead of strong form, you had weak form. We did this intermediate step. Instead of that weak form, you have that. And now instead of that, you have this equation. And in this equation, all you see are just parameters that we will talk about in a second. So we need to solve this equation. All right, so let's say we have this equation. We know left-hand side must be, let's say, equal the right-hand side. So this is our equation. And we need to solve this. So remember, we did something like this when we dealt with a linear function, but we didn't have a big problem there because there, when we had this, we had a slide like this. So there, when we wanted, or when we wanted to solve this, we basically had one equation, one unknown. Okay, so when we did this previously, the only unknown was d1, and then one equation was enough. Now I look at this. This looks like one equation. And I put a question mark because we should ask ourselves, is it really a one equation? Or is it really one equation? So it looks like one equation, but we have, let's say, 4 unknowns if you want. Okay, so if you just look at what you have in front of you, there is C1 and D1, and then there is E1 and F1. Okay, and remember, if you know E1 and F1, by the way, you would know F2. So in other words, if you could actually solve this, it would help. So these 4 parameters, if you could solve it, you know the solution. So this is really what we need to do next. We need to find a way to solve this. Now here, the important step is to pay attention that this equation is not one equation. Okay, so I'm going to write this here. This, I don't know, maybe it seems like one equation, but it's not. Now, this is very important because as I mentioned, for the next examples, I'm not going to go through the steps one by one like this, but this point where you end up with an equation which looks like one equation and you need to solve it, this always repeats. So at this point, you need to do something else. You need to pay attention to the problem and, let's say, devise a nice strategy to proceed. Okay, the strategy you have to, let's say, take here to proceed is not very difficult. It's all in one, let's say, word. It's here. Remember we said W is arbitrary? This is all that matters for you. So basically, because W is arbitrary, and remember these coefficients, again, E1 and F1, these are the coefficients that come from displacements. But C1 and D1, these coefficients, they come from the definition of W, or from the W approximation. So if you know W is arbitrary, you know C1 and D1 are arbitrary. So that's the key. W is arbitrary. That means C1 and D1 are also arbitrary. So this equation must hold for any C1 and D1. And that changes everything. That changes everything, because now, I mean, it depends how you want to look at it, but one simple way of looking at it is to pay attention that, for instance, you can imagine that one of them is 0 and the other one is not. Okay, so if it holds for any, if it holds for any C1 and D1, it would also hold for C1 equals 1, D1 is 0, and then C1 is 0, and D1 equals 1. So it holds at least for these two sets too. And then basically, if you just play that game, you can simplify this further. And that's what I'm going to do now. So let's say, first assume C1 is 1 and D1 is 0. Second, assume C1 is 0 and D1 is 1. Now, okay, maybe I do it like this. So from the first one, if you assume D1 is 0, these terms will disappear. This will go away. So if D1 is 0, you would only have this one, and then this C1 is, by the way, also 1. So you would get like 1/2 of E1 here. You would get 1/8 here, plus 1/4, which is 2/8. So that would be 3/8. Okay, so basically your first equation would look like 1/2 E1. I bring 3/, so this, you'll get this basically, but I write it on the, I bring 3/8 to the left hand side for, let's say, for sentimental purposes. It looks nicer, I think, if everything is equal 0. And then you do the same thing, you play the same game for the second set. So now if you assume C1 is 0, these terms disappear, and D1 is 1. So this one gives you just 1/2 of F1 basically. And the second term gives you plus 3/8 minus 1/4, which is 2/8. So that would be plus 1/8 on the right hand side. So on the left hand side, if you write it, it would look like this. So the second equation would be 1/2 F1 minus 1/8 is 0. Okay, so this is now two equations, two unknowns. I mean, in this particular case, these are two individual equations, and you can compute each unknown from its own equation, but it may or may not be like that. So later you may have actually complex systems that you need to solve them together to find the coefficients. But in this case, this is basically your usual two equations, two unknowns. If you solve them, you can calculate that E1 would be 3/4 and F1 would be 1/4. All right, So I'm going to just clean up what is not necessary here anymore. But let's see what we have now. We have these approximations of U. They have unknown parameters E1, F1. And then again, once you calculate E1 and F1, you know what is F2 from this equation. And now you have E1 and F1. So that's it. Now we actually have the solutions or the approximate solution for U. So you can say that if X is between 0 and 0.5, so in the first half, and in the second half, you can just insert those parameters and you would have your displacement function U. So E1 is 3/4, and that is basically your U for the first half. For the second half, U would be 1/4 X plus 1/4. So E1 minus F1, yes, E1 minus F1 is 2/4, and then you have a 1/2 here. So F2 is also 1/4. All right. Okay, so now that we have this, I'm gonna just remove the additional things here. And we can sort of draw this function together and see how it looks, but also later I'm going to just draw the, I'm going to draw the analytical solution on top of it, or I'm going to draw it together with the analytical solution. But just before doing that, let's identify how this thing is going to look like. This is going to be a line starting from 0 with a slope of 3/4. Okay, so it would look like this. Let's say it has a high slope, and then at x equals 1/2, it would it would hit like 3/8. Okay, now after that, it would be a line with a slope of 1/4, which at 1 it hits 1/2, which is 4/8. So this is, let's say, let's call this 4/8. Let's call this 3/8. So this is going to be your approximate solution. There is a, let's say again, there is a first line with a high slope until here, and then it's continuous at that point. And then you have a line with a slope that is 3 times less, and then that would be your solution basically. Now, you can easily check that this thing is continuous. Again, if you measure this, if you just evaluate this thing at 0.5, so if you say x equals 1/2, then you can see that your first u would be 3/8, and your second u is also 1/8 plus 1/4, that is also 3/8. So the continuity at the center or at 1/2 is satisfied. Okay, as promised before, I'm going to now draw this line on top of the analytical solution, and I'm going to do exactly the same thing we did with this linear function. Remember, for the linear function, we played the same game. So I just sort of copy this information from the linear function and try to draw, let's say, the new function on top of it, if I can. All right. Okay, so you remember this was what we had before. The orange function is the approximate solution. It's a linear approximation. So I call it now linear approximate solution or one piece. Okay, it's a one piece linear approximate solution. What we have now is a two piece linear approximate solution. And this would be the gray function in front of us. So if this is the center, basically your line, the new line, this function that you have that we talked about is this. Let me see if I can make that more clear. So that's the first line or the first piece, and that is the second piece. All right. Now, if you look at these points, you can sort of see a similar story as before. Again, let me just clarify that this is the first line. This is 3/4x. And this is the second line. And that is 1/4x plus 1/4. And as I mentioned, if you look at this now, you see a similar story. First, the Dirichlet condition is satisfied strongly. So we hit at 0, we hit the boundary condition, what we expected. You hit the solution at the nodes. So we get this thing that we usually refer to as super convergence. So the approximation is, let's say, is gone or is much less at points. In this case, it's completely gone. So it is a super convergence. And then you have this other thing that basically at the Neumann part, the boundary condition is not satisfied exactly because the derivative is not 0, but you see the derivative is closer to 0. So this is your analytical solution. You want to have a derivative 0. A linear approximation gives you a line with a slope of, let's say, 1/2. Now you have a line with a slope of 1/4. So it's a closer approximation at the Neumann condition too. All right. So this is kind of the game that we played so far. We had one piece linear and we had two piece linear approximations, and we did them among many other tasks that we had to do. So we did this before. That's a one piece linear approximation. And we just did this two piece linear uniform approximation. So uniform in the sense that the point was exactly in the center. What we want to do next is to do a two piece linear non-uniform approximation. And we take two different points for the non-uniform one. One time we take a point that is slightly to the right, and one time we take a point that is slightly to the left, so that we can compare them. And then looking at them, we end up with this sort of generic view or unified view that allows us to generalize this to a, let's say, a general approximation for let's say for two piece linear functions. So we can calculate that as a function of the coordinate of this point. Okay, so it would be a generic approximation of that. And after we are done with that and we get this, let's say, unified view, then we play with a three piece approximation. And we do it first uniformly, and then we do it generically. And then we do the same game for a four piece approximation. Then we do a quadratic approximation, and we do a cubic approximation. As I mentioned, this is like a very long exercise to explain what's going on in the, let's say, in the finite element method methodology part. But the story is not that complicated. There is a lot of mathematics in between, or mathematical steps, but the important story is simple. Strong form here, the strong form that you have is a differential equation. Your weak form is an integral equation. And in this integral equation, you have lower derivatives of u. So basically, instead of having a quadratic function, you are allowed to have piecewise linear functions. And then if you want to calculate those piecewise linear functions from the weak form and from the, let's say, from the conditions that we have on the test function, it seems it's working. And it gives you a very decent approximation all the time. So we looked into 2 examples. They give good approximations. What we want to do next is repeat the same thing for a generic, for a non-uniform approximation using a 2-piece linear function. So I'm going to now clean this. And I keep using the same slide because I want to kind of keep reminding you that this is exactly the same problem, only the details start, or the details will change. So here the word uniform would be non-uniform. And then I'm going to, so the word uniform would be just non-uniform here. And what we need to do here is to just assume that the point that we had previously at the center is no longer at the center. So what we want to do is, coming back to the example we had, again, with the point at the center, remember this was kind of how we did it. We do exactly the same thing. So I'm going to copy, let's say, this part about the domain. So this was the domain that we started with. But now all that is going to change is that instead of 0.5, which made it very nice for us because it was exactly in the center, I am going to choose a point that is slightly off center. So let's use 0.6. The question is, if we are off center, do we also get that super convergence? Do we also get those nice property that we got previously? We want to do this next. All right, so it's exactly 9:22. So let's have a 10-minute break. I will see you at 9:32. All right, so what we want to do now is to look into this equation. As I mentioned, now the midpoint, the point between 0 and 1, is not exactly 0.5, it's 0.6. But the intermediate steps are very similar. So I'm going to sort of write it in a similar manner, ideally using the same notations and even colors. So W now, remember it was C1x plus C2. This is exactly like before. U is E1x plus E2. In the second piece, W is D1x plus D2. And U is F1x plus F2. Now, if you remember from the boundary condition, we said, well, E2 is 0. You can see it here because U at 0 is 0. But also because it is a Dirichlet type boundary condition, C2 is 0. Then if you impose the continuity condition for the W at 0.6, you can calculate D2 to be 0.6 times C1 minus D1. And the same holds for F2. So F2 is 0.6 E1 minus F1. Okay, so everything that we have here, we also had it before. I mean, we wrote it in, let's say, or we went into more details, but this is exactly the same thing. Remember, if the point was in the center, again, these two were 0, W at Dirichlet was 0, and then we had these relations between D2 and F2. So these are similar relations, but here we had 1/2. In the next example, because the point is not at the center, it turns out that coefficient is 0.6. So that's that. Now, the next thing you need to do is to proceed with the integration. And for the integration, you are going to split the integral now from 0 to 0.6, and then from 0.6 to 1. So it's exactly the same integral as we had up there. Dx equals integral w all right. Now all you have to do is play exactly the same game. Remember, we said this, so w prime from 0 to 0.6 is c1, u prime is e1, here w prime is d1, u prime is f1, then w here from 0 to 0.6 is d1, sorry, it's c1x, and from 0.6 up to 1 is d1x plus c1 minus d1. 0.60 c1 minus d1, sorry. So that's that. So basically all you have to do now is to just use these values and do the integral. And that's what I'm going to do next in the next slide. So I will just copy this, replace this in the integrals, and proceed with that. Okay, so in the first integral, you would have c1 e1. In the second integral, you would have d1 f1. Okay. In this integral, you would have c1x. And then in the last integral, you have exactly the blue term that we have at the bottom. Maybe I put them in big brackets for clarity. All right, so that's that. And that's d1x2. I also changed the color to white so that it's clear. Okay, so this is exactly the integral. Now you have to calculate, and if you do that, and you play with the, let's say, terms a little, I put 3 dots here. I don't go through that intermediate step. You end up with this equation. It's going to look like C1 0.6 E1 minus 0.42 plus D1 0.4 F1 minus 0.008 equals 0. Okay, so this is your integral basically. And all we have to do is to calculate these parameters. Now, as I mentioned, from your integral to this, there is just one little step, which is purely mathematical, to arrange the terms so that they look nicely like this. But you don't have to worry about that. So basically, eventually this is the equation you are gonna get. And what we want to do here is to calculate the coefficients E1 and F1, remember, as before. Now you see the reason why I ordered the term nicely, because we play exactly the same game. This looks like one equation, and then we want to calculate different unknowns from it. But it's not exactly that. It is one equation, but because W is arbitrary, this holds for every C1 and D1. And now if you look at it, because it is nicely sorted, you can see if something is equal 0, and then it holds for every C1 and D1, that means each of these terms, they must be 0. And this is exactly your two equations that you want. Okay, so this is again the same story that we played before. This looks like one equation. We played this game also here. If you look at this, this looks like one equation, but because it holds for every C1 and D1, it is more than that. It gives you more information, and essentially it tells you that each of these terms are 0. So here I didn't order term nicely so that we didn't see them as coefficients, but here you can see those terms, they are basically the coefficients of C1 and D1. So again, because these are arbitrary, each of these must be 0, or otherwise you can imagine that this is 0, this is 1, so this has to be 0 then, something like that. All right, so that's all you have to do basically. Here you do that, you write this equation. Let me also then clean up a little. And this is the equation you have. Sorry, yeah. Let me just keep it. I want to do exactly the same thing as I did before. So let's forget the W part, because you can see W is just an accessory for us. Okay, it disappears. It's just an arbitrary function. You multiply it, it does its job, and then it's gone. So that's exactly how we look at that. So again, you have this two-piece problem, and now this is your equation. This thing plus this is equal 0, and that tells you that, let's say, because it holds for every C1 and D1, then that tells you that E1 is 0.7 and F1 is 0.2. Okay, now if you insert these into your U, you can see that U equals then 0.7 times X for X between 0 and 0.6, and then from 0.6 to 1, U is equal 0.2x plus 0.3. Okay, again, it's a nice game if you just play what would be U exactly at X equals 0.6. So if X is equal 0.6, the first one would give you 0.7 times 0.6. That would be 0.42. The second equation gives you 0.2. Yes, 0.2 times 0.6, so that is 0.12. Sorry. What is wrong here? I might, let me just check again. Yes, it's correct. Sorry. Yes, so this one gives you 0.42 at x equals 0.6. This one also, so this would be 0.12 plus 0.3. So that is also 0.42. Okay. So it's correct what I have written here.
Hocam, can I ask a question real quick?
Yes, please.
Hocam, I think
Yes,
we
please.
made a mistake 0.008 part in the 0.4 f1 minus 0.008. Because
Yes,
when we
there is.
multiply 0.2 times
Yes,
0.4
yes.
should be.
There is 1 0 extra.
Yes.
Thank you very much. Yes. So, yes, so this would have been 0.08. Okay. Thank you. Any other question? Very good. So anyway, this is the game that you are going to play. And eventually, if we plotted this, by the way, I'm going to do that just now. If we plotted this like we did previously, we would end up with very nice, again, another nice approximation. It's just not hitting, or it's not going through the center anymore. So basically, if you just take this, now this is the solution here, and let's remove these ones. I'm going to also remove this to make more space. If you remember the solution we had here, and now we want to, let's say, draw this on top of that. I don't know how complicated it gets, but let's try. Okay, it's not too bad if I clean these additional parts. So now what you have here, you can basically look at it in a similar manner. You had a one-piece linear, you had this two-piece, and what we want to do now is to look at another two-piece, which is not going through the same point as before, but eventually it's a similar story. So I don't know, if we assume this one is, let me use a different color, maybe red. If this is now a red function, this point that we looked at, it would be this, would be 0.6. And then for the red function, it's going to look like this. Again, it would be a line that hits the, let's say, the first point, the Dirichlet condition. It hits the analytical solution at 0.6, and then it has this additional piece, which is another line with a much less slope. So if you look at this now, the slope of this one is 0.2. So remember about the slope at the, let's say at the end, the analytical solution, the slope at the end was 0. For one piece linear, it was 1/2. For two-piece linear, it was 1/4, which is like 0.25. Now for this one, it's 0.2. So it's 1/5 basically. Okay, so you see, basically the approximation at the other end is getting better because the point that you chose is closer to that end. If instead of that you chose a point in the other part, maybe you can imagine that you would get a worse approximation at the end, and that is something we are going to just look at now. So this is the key idea. You can do this multiple piece approximations, and now, as I promised, we are going to do the same thing for a different function. So back to our agenda, we had done this, we just did this. So it's a non-uniform approximation, it's a two-piece linear. We are going to do the same thing again for a different point, but now for this one, I'm going to take the point on the left side of the center, so not at 0.6. I'm going to assume that point to be at 0.4. Okay, so it is on the left side, basically. And I'm going to use a similar slide. So basically, I just use exactly the same slide to highlight the similarities. So you see these 0.6 numbers here? They will consistently change to 0.4, and that's really it. Okay, so that's all you have to do. Now, if you imagine this is your domain, again, from 0 to 1, we have done this approximation, assuming that the midpoint is at 1/2. We have done it previously, assuming that that point was at, let's say, 0.6, and now we will do it at 0.4. This is what we want to do next. And as I mentioned, in order to do that, if you could exactly follow what happened previously, this is going to be easy. All you have to do is to just change these 6 everywhere to a 4. So this would be a simple way of rewriting it. But obviously you can and should write it on your own neat and clean to understand it. But if I haven't made a calculation mistake, this is how it's going to be. Okay. So this is your next one. Now, I want to solve this. And in order to solve this, I'm going to also use, again, the same slide as we did previously, and I change only 0.6 on that to 0.4. So remember, this was basically that slide. I mean, we had that intermediate step, of course. I can also write the intermediate step if you want. You would have a similar intermediate step like this. But eventually, you would get the same equation. Let me also write the intermediate step because it helps you possibly for checking your calculations. So if you did this intermediate step, again, this would be 0.4 here, here, here. And these coefficients will change, but the overall strategy remains the same. So if these are 0.4, please feel free to correct me if I make a mistake. As you can see, in order to save time, I'm just using the similarity between the slides. And I think that's a very good way of looking at it, because that is eventually the message I want to pass here, that there is indeed a similarity of the strategy. So if you do that, you would see this, and then here you would get 0.6 minus 0.18. And then again, the same game is played. So this looks like one equation, but because it holds for every C1 and D1, it means that these coefficients should be 0. And I missed, of course, some numbers there. So that would be 0.4 E1, and that is 0.6 F. Okay, so this is what you get. And then again, I will just use the previous slide. Even I'm going to show something else here. So this would be 0.4, 0.4. This is going to be 0.4, and then here the coefficient is 0.4 E1 minus 0.32. It will be 0.6 F1 minus 0.18. So instead of 0.8, it's 1.8. And then again, because it holds for every C and D, then you can calculate E1 and F1. So if you do that, E1 would be 0.8, F1 would be 0.3. And if you insert this into your equation, basically your first piece would be 0.8 times X. Your second piece would be 0.3 X plus 0.2. Yeah. And then again, you can play that game, or to check if at X equals 0.4, this thing is continuous. And if you play that, you can see it. So 0.8 times 0.4, this gives you 0.32. But also 0.3 times 0.4, that gives you 0.12 plus 0.2, that gives you also 0.32. So this is indeed continuous at 0.4. All right, the last step you want to do is to draw this. And in order to do that, I'm going to, again, use the same slide as we did before for the similarity. But now, let's say we had that red line. It's getting really complicated, as you can see, but it doesn't matter. I just want to pass the more important message. Now, if that point that you chose is on the right, on the left-hand side of 0.5, so it's here. Now, the line you have is going to be this piece first. And the second piece would be this one. Okay, and then again, it also hits the solution. So this would be now your new approximation. It's another two-piece approximation. It's a uniform approximation. But here, just to make this picture even more complicated, I want to highlight that difference of tangents at the Neumann boundary condition. Again, Dirichlet boundary condition is strongly satisfied, so that's not a problem. But you can see that the Neumann part for the analytical solution, you know the Neumann part is 0, the slope here is 0. Okay. So the slope here is 0, but if you did a two-piece linear, you get a better approximation compared to a one-piece linear. For a one-piece linear, the slope that we got was 1/2, right? You can see it clearly here. For a two-piece uniform, the slope that we had was 1/2 of that. So it was sort of 1/4 or 0.2. When we had this two-piece linear approximation, but the point was on the right-hand side, we had even a better approximation. So we had 0.5, if I'm not mistaken, in the previous one, which, sorry, 1/5, which is 0.2. And that was 1/4, which is 0.25. And now if you look at the approximation we just had, it is on the other side because the point that we chose, it is on the left-hand side. So it kind of, it sort of reads more information about the first piece than the second piece. So the slope, if you look at it from the one that we have now, is 0.2, okay? What's that? It should be 0. Yeah, it's 0.3. Sorry, I didn't write it here. So this one is 0.3. Okay, so the blue solution that we don't have on this slide is u is 0.8 times x, and for the second piece is 0.3x plus 0.2. Okay, so basically you kind of get a feeling of how things are going here. I know this slide got very say confusing and complicated. I'm going to clean it up in the next slide, but I just want you to have this sort of bigger picture. So let me just summarize this quickly. So we did one piece linear approximation, we did two piece uniform, and we did two pieces also that are non-uniform, and we kind of compared it how this non-uniformity could help us capture the behavior of a function. Now, if I want to put all of them in one graph, and that's what I want to do next, it's going to look like this, what we have so far. Let's say this is the vertical axis, maybe here. This is the horizontal axis. And imagine you have this analytical solution that is a quadratic function and is also going to be 0 at 0. So it looks like this. This is assuming that this is your analytical solution, which, by the way, this is a luxury, right? So you understand that the analytical solution doesn't exist in general, or we don't know the analytical solution in general. This is just a reference solution for us to compare to the other solutions. But this is a luxury, right? This doesn't exist in let's say in reality. So if you run a numerical simulation, you never know where the solution is. You just get your own approximate version of it. And as I mentioned now, you know those approximation. Let's say if we assume that point was in the center, you get an approximation which looks, or you get a two-piece approximation which looks like this. Okay, so that would be a two-piece approximation if it was uniform. So let's say this is 1/2. Maybe I call it just 0.5. If you had a one-piece approximation, this would be just a straight line. Okay, so this is your one-piece approximation. So this is one piece. Orange is two-piece uniform. Then we had the other one. I think we had the point on 0.6. Let's say it's here maybe. And again, if you had that, it would have been also basically two pieces, two lines. These are still linear approximations. So the first line would be here, the second line would be here. And then again, if you had just that point on the left-hand side, maybe if it is 0.4, this would look like this. You can, and I think it would help you, and you should plot this in MATLAB to or some other software to get a good feeling about this. So we have the functions anyway, and you can basically make these plots. Okay, so this is what we have so far, and we want to play with this a little more and do other approximations. So this one was a two-piece. We called it non-uniform one, I think. And then we had the blue one. That's this one. And that is a two-piece non-uniform two. Okay, so I mean, we had some mathematical steps, but I think this is important that you see this bigger picture. But also more importantly, I want to, again, let's say I copy this, I replicate this. I want to emphasize that this thing, the analytical solution doesn't exist. So usually you are talking about something like this. You don't know where that analytical solution is. You just know that you have these solutions. Okay, so this is a better picture of how finite element works for you. Okay, so the gray solution is just something that we do not have. Now, what we want to do next is to play with this again and proceed with other parts. So we have done these. Now, based on what we have done, we want to just derive a two-piece generic approximation. Okay, and I think based on what I just did, you can have a good feeling how it's going to go, because you saw that when I changed from 0.6 to 0.4, it was basically changing some numbers. So I'm going to do exactly the same thing. I start from what we just had for 0.4. So here, but I don't want to do this non-uniform approximation. I want to do, well, it is also non-uniform, but here the word here is generic. Okay, generic in the sense that I am not going to say this thing is 0.4 anymore. I just call it A. Okay, it's a point at coordinate A, and A could be anywhere between 0 and 1. So it turns out if this thing was A, and then again, maybe you have a good feeling about it because we just saw about what happened to 0.4 and 0.6. If you had A, the coefficients here would be just A. Okay, so the boundary conditions again are imposed and the coefficients are here. And then when you want to integrate this, all you have to do is to replace this 0.4 in your integrals with A. So this is what you have. And basically what that means is that now the point you are talking about is a point, let's say here or here. It doesn't matter. It's just the distance A, and A is any number between 0 and 1. So if you do this, and if you do the integral, you get the following. Let me just do that. So basically, after proceeding with this and after writing the integral, you get a term which looks like that. you get an equation. It will look like A1, C1, E1 plus 1 minus A D1 F1. You can identify the terms, by the way. This thing is exactly what you would have here from the integral in the first part from 0 to A. And this thing is what you would have from here from the integral from the second part from A to 1. So that would be equal. And then you would do the integration for the right-hand side. Now also for the right-hand side, again, remember this integral won't be just 0 to 1. It would be from 0 to A plus from A to 1. So you would expect to get two terms. So you would get, let's say, a term 1, which I'm going to skip, plus a term 2. And after you do some, let's say, mathematical steps, these two terms can be split into, or let's say combined into something which would look like this. AC1, 1 minus 1/2 of A plus D1 times 1 minus A times 1/2 minus 1/2 A. Okay, so essentially this is again your equation that we need to solve. And as we have played this game many times now, we know the trick to solve this equation is to take into account that these coefficients C1 and D1 are arbitrary. So this thing holds for any C1 and D1. And basically from that, you can solve the coefficients. And if you do that, E1 would be 1 minus 1 over 2A. And F1 would be 1/2 minus 1/2 A. Okay, so all you have to do next is to insert these values into your displacement function, into your U function. Remember, U is just a function of E1 and F1 basically. And now you have these coefficients, you have the parameters you wanted in the first place. So that's what you're going to do. And then again, I'm going to remove W. W is just an accessory again. It's for us to solve the displacement, or to solve for the displacement. And now that we have that, we can say if X is from 0 to A, displacement would be 1 minus 1/2 A times X. And if X is from A to 1, then U is 1/2 minus 1/2 A times X plus 1/2 A. Yeah, and that's it. So you can play the same game that we played before. We want to check, or we want to make sure that these two pieces at X equals A are giving the same answer. So at X equals A, the first one gives you 1 minus 1/2 A, well, A times A. The second one gives you 1/2 minus 1/2 A times A plus 1/2 A, which if you compare them, you see they are also equal. So you have this minus 1/2 A squared in both terms plus 1 A. Okay, so it's 1/2a plus 1/2a downstairs, and then upstairs is just 1a. So they are also continuous, so that continuity condition is satisfied, which we wanted. And now that you have this, it's very nice, because if you just look at it, it's exactly what we wanted, and everything we did until now was to come to this generic form for a two-piece linear function. So now I want to, you know, for the fun of it, let's play our game that we did before. Let's assume a is 0.5, so it's in the middle. In the second one, I think we assumed a was 0.6. And in the third one, we assumed a was 0.4. So once you have it for a generic a, for any a, you can just insert those a's and check your solution. So if you insert a equals 0.5, and you compare these two solutions, so you get 1 minus 1/2 of a, which is 1/2 of 0.5, or 1/2 of 1/2, that is 1/4. So that gives you 3/4. So that would be 3/4x. And the second one would be, let's say, 1/4x plus 1/4. Okay, and this is, if you remember, this is something we had in our previous slides. So I don't know exactly where, but somewhere here you see that, or you see the same equation here. So earlier today we saw these basically. This is exactly the same thing, and now we have the generic form. So all you have to do is to insert that number, and you get that generic form. Then we have it for a equals 0.6. So in this case, u would be 0.7x up top, and then u equals 0.2x plus 0.3, which again is something we just had slightly after that. So I think, yeah, it's exactly what we had here. So this was for the case where a was 0.6, and then eventually if we now insert a equals 0.4, we get these two. So u equals 0.8x, and u equals here 0.3x plus 2. All right, now if you kind of look at these numbers, just to make it more interesting and more maybe reminding you of something, let's say instead of 3/4, I'm going to write 0.75x. And here downstairs, I'm going to write 0.25x plus 0.25. I mean, if you just look at the numbers, maybe you can see something interesting for you, or you can try to digest the meaning of these approximations, or how the point will change the solution. So let's say at 0.5, you have 0.75, and now you get minus, you see, it's like basically these two numbers are 0.75 plus minus 0.05. So sort of the slope of the line is basically changing in a, let's say, in a uniform manner, apparently, or in a linear manner. And then a similar story happens with the coefficients here. You can see that, let's say, by deviating from the center, a similar thing happens also on the right-hand side. So if you go towards the right part, the slope will decrease for the second part, right? The slope will decrease, which we kind of explained why it happens, because you want to get a better approximation of Neumann type boundary condition. If you move towards left, then the slope increase, which gives you a, let's say, a worse approximation of the Neumann condition at the end. So this is sort of the big message. We are going to unify this even further more. So next time I'm going to also explain this in terms of the slope of the line. So I think this is where I want to lead. You should pay attention to the slopes more than the coefficients, that they remain in addition to. So the slopes have a story to tell us. Okay, so the approximation is closely related to how the slopes are playing their roles here. All right, so just to wrap it up, we have done, let's say, the first part completely. I am going to continue on this. I will just explain this in terms of slopes at the beginning of the next lecture, and then we continue with these ones. As you can imagine, since now we have established this framework, we can proceed much faster in the next lecture. I'm not sure if we can finish it in the next hour, but we will finish it in the next 2 hours, definitely. And then after that, we proceed with the rest of the journey and the rest of the map that we had started from. All right, thank you very much for your attention.